Next, we're going to talk about vertical and horizontal asymptotes. Now, this is actually a topic I meant to cover before Exam 1, but when I made the video, I decided not to post it because it would have, I think, made one of the weeks have more information than I wanted to put in 1 week. And then I, after that, planned on putting it on Exam 2, in particular week 4 between Exams 1 and 2. But during that week, I forgot to attach my microphone. So now here it is, right after Exam 2. So for vertical asymptotes, well, we'll start with the definition. We've seen vertical asymptotes before. We might not have called them that. We might have. I don't particularly remember. I think I did call them that. Definition. X equals a vertical line, is a vertical asymptote for f of x if the limit on the right of a is positive or negative infinity, or if the limit on the left of a is positive or negative infinity. So for it to be a vertical asymptote, all we actually need is one of these 4 limits to be satisfied. For most of our examples, we'll have one of these and one of these satisfied. As in this example, f of x equals 1 over x minus a. Well, we know how to graph that using a graph transformation, but that function has a vertical asymptote over here at x equals a. And you'll notice on the right of a, the limit is positive infinity, and on the left of a, this limit is negative infinity. Now, the functions we're going to find vertical asymptotes for are largely going to be fraction functions, meaning rational functions, p of x over q of x. Now, here I'm being a little informal in this remark. We're going to assume that this means it is a fully reduced rational function, meaning you can't factor the top and bottom and then cancel it out, cancel something out. But for rational functions, there is a vertical asymptote when the denominator equals 0. Now, that's for rational functions. We could also throw a square root on the top or the bottom, and the same result holds where there is a vertical asymptote where the denominator equals 0. So vertical asymptotes, we will find that finding vertical asymptotes is not a difficult algebraic computation. We won't need to prove vertical asymptotes by going through a limit argument. This is just to define it formally. But horizontal asymptotes are a little more subtle. Now, for horizontal asymptotes, a horizontal asymptote can describe behavior as a function goes to positive infinity or as the function goes to negative infinity. In either direction, you could approach a horizontal line. So to define a horizontal asymptote, we need to consider the 2 limits. If limit as x goes to positive infinity is some number, call it L1, or if the limit as x goes to negative infinity is some other, potentially other number, call it L2, then f of x has horizontal asymptotes y equals L1 and y equals L2. Now, to find horizontal asymptotes, we will have to compute both limits if we don't already have a graph. But for this first example, I'll just give you the graph for this function. Now, you could actually figure out this graph using the tangent graph and then flipping it over the line y equals x. But we haven't discussed this graph to this point, so I'll just give it to you. F of x equals the inverse tangent of x. Has 2 horizontal asymptotes. So right here we have inverse tangent of x. As x goes to positive infinity, this function goes up toward the line pi over 2. As x goes to negative infinity, this function approaches the line negative pi over 2. Y equals negative pi over 2. So from the graph, we found the 2 limits. As x goes to positive infinity is pi over 2. We found the limit as x goes to negative infinity is negative pi over 2. So the inverse tangent of x has 2 horizontal asymptotes, y equals pi over 2 and y equals negative pi over 2. Now, for the functions we will be seeing, if you're asked to find horizontal and vertical asymptotes, well, if you're asked to find horizontal asymptotes, you'll have to compute two limits. And we know how to compute limits to positive infinity. We actually know two different ways that we can compute a limit to positive infinity. We can do it as we did a few weeks ago by dividing everything by x to the largest exponent on the bottom, or we can actually use L'Hopital's rule if the function has a form of what? Negative infinity over infinity, or positive infinity over infinity, and so on. But limits to negative infinity, to this point, we actually know only one way to compute a limit to negative infinity, and that's using L'Hopital's rule. And we'll see that using L'Hopital's rule on some functions leads to very unpleasant computations. So how do we compute limits to negative infinity? Well, first you could use L'Hopital's rule. We won't do that for this video. Let's see if that stays. So 1, L'Hopital's rule. Now I could give you questions where using L'Hopital's rule is quite complicated. I could give you questions where using L'Hopital's rule for the limit to negative infinity is moderately complicated. But there is another way. So let's say this other way. Now what will we do? We will apply a graph transformation. So I'm just going to say way 2 is apply a graph transformation. Now, which graph transformation? Well, there are a lot of graph transformations you could use. Most of them will not make the computation much easier. But there is one we can use that will make our computation easier. And I think I'm going to need 2 boards to do this. So let's erase this board. So a limit to negative infinity describes behavior. Let's draw a graph. Or let's draw an xy plane. The limit to negative infinity is concerned with behavior of the function as x goes toward negative infinity. So as x is going in this direction, the limit to negative infinity is going to figure out what happens in this direction. Sorry, I just got distracted by a noise. That's actually the heat turning on. I'm going to turn that off. It's a little cold here tonight. I think it's like 25 outside. So I put the heat up to 59. Where was I? A limit to negative infinity describes the behavior of the function as x goes to negative infinity, as x goes in that direction. We know how to compute limits to positive infinity. We know how to compute limits in that direction. Without L'Hopital's rule, we know how to do that. By dividing everything by x to the largest exponent in the denominator of our fractional function. But we also know a graph transformation that can take what happens over here and flip it across the y-axis. So we can apply, let's change this to the graph transformation now. Apply the graph transformation that flips the function across the y-axis. Because if we flip it across the y-axis, then this behavior will now happen over here. So let's say now happens here. So this behavior now happens there. What transformation will flip it across the y-axis? Well, we take all of these x's and replace them with negative x's. So the graph transformation x goes to negative x. If you do that, the function will flip across the y-axis, and then the behavior as x goes to negative infinity is now captured by the behavior as x goes to positive infinity in the new the newly transformed function. So how to compute limits to negative infinity? 1, you could use L'Hopital's rule. 2, you could apply this graph transformation and compute, let's just say, limit as x goes to positive infinity of whatever our function is. And we're going to do 2 examples of finding vertical and horizontal asymptotes. In one of these, well, in both of them, I'm going to go through this process. But in both of them, you could apply L'Hopital's rule. So first, let's look at this example. Find the vertical and horizontal asymptotes for that function. Well, let's start with the vertical asymptotes. For the vertical asymptotes, well, let's set the denominator equal to 0 and then solve. How do we solve this? Well, let's factor out an x. 2 things multiplied equals 0 exactly when one or the other is 0 in the real number system. Add 5x, divide by 5. So we get x equals 0 and x equals 4/5 are the vertical asymptotes. Vertical and asymptotes are both quite large words, so we'll just abbreviate them VA. Well, that's great. We already found all of the vertical asymptotes, so now let's find the horizontal asymptotes. Well, to find the horizontal asymptotes, we need to compute 2 limits. Well, let's start with the limit to positive infinity. Limit as x goes to positive infinity of 2x squared minus 3 over what? 4x minus 5x squared. Well, you could use L'Hopital's rule because this is what? Infinity over negative infinity? I'm just going to multiply by 1 over x squared over itself. And then simplify. We get limit as x goes to infinity of what? 2 minus 3 over x squared all over 4 over x minus 5. And this, of course, equals 2 minus 0 over 0 minus 5, negative 2/5. Well, that's great. We have one of our horizontal, well, we have one of our limits. So we have a horizontal asymptote. Well, what we need to do next is compute the limit as x goes to negative infinity. I should write that so it looks a little better. So we did one limit. Now we have to do the limit as x goes to negative infinity. Limit as x goes to negative infinity of 2x squared minus 3 over 4x minus 5x squared. Now, we actually could, for this example, jump straight into that first step and apply reasoning using x going to negative infinity. In the next example, that process will be a little more complicated, and the graph transformation I described earlier will be easier to see. Well, it'll be easier to see. Well, what will it be easier to do? If we applied the reasoning we could apply here to the next one, it would be very easy to make a mistake in the next one. So we won't immediately multiply by something like this. What we'll do instead is transform this function, transform this limit into a limit as x goes to positive infinity. And how will we do that? Well, we replace all x's with negative x. Did we replace all x's with negative x? Because notice we have limit as x goes to negative infinity here. We have limit as x goes to positive infinity there. So we better have replaced all x's with negative x. Well, replace an x with a negative x in the numerator, you get the same thing. Because negative x squared is just x squared, and then the 2 and the negative 3 carry along. But notice in the denominator, this 4x, if you replace that x with a negative x, 4x becomes negative 4x. And then negative 5 times x squared, like that piece in the numerator, remains the same because negative x all squared is x squared. Well, now we can treat this like a limit to positive infinity. You could use L'Hopital's rule twice. I don't want to do that. Or you could multiply everything by 1 over x squared, the largest exponent in the bottom. You get limit as x goes to positive infinity. 2 minus 3 over x squared over negative 4 over x minus 5. And this also equals 2 minus 0 over 0 minus 5, which is negative 2/5. So we found the two limits. We can reach our conclusion. So f of x, well, I'll say, I'll use the same phrasing I used over here. So y equals negative 2/5 is the, notice these two limits are the same. That can happen sometimes. So y equals negative 2/5 is the horizontal asymptote. So here we found all of the asymptotes, all of the horizontal and vertical asymptotes. And next, we'll look at this example. Find the vertical and horizontal asymptotes for f of x is root 2x squared plus 5 over 4 minus 3x. Well, again, I'll start with the vertical asymptotes. Set the denominator equal to 0. Add 3x, divide by 3. So x equals 4/3 is, in this case, 1, so we'll say is the vertical asymptote. Now for the horizontal asymptotes, we again have to compute two limits. Limit x goes to infinity, root 2x squared plus 5 over 4 minus 3x. Well, here we have effectively a degree 1 in the top and a degree 1 in the bottom, so we'll divide everything by 1 over x because of that bottom. And remember, to get that x inside this square root, we need to consider it as a square root of x squared, which we did in week, I believe, 4. So this equals limit as x goes to infinity of, what, 2x squared over x squared plus 5 over x squared, square root of x squared, to get inside the square root, all over in the bottom, 4 over x minus 3. Now, as x goes to infinity, the numerator goes to root 2 plus 0. Denominator goes to 0 and a negative 3. So we get negative root 2 over 3. Well, that's great. Now we need to do the limit as x goes to negative infinity. Now notice, for the limit as x went to positive infinity, you could have applied L'Hopital's rule, and then you'd get, well, you'd have to apply it a couple times. I think that would work. It should work. Maybe I should actually go through that on the side to be sure that it works. But dealing with the derivative of a square root requires a chain rule. And because of that, and in the back of my mind, I knew that this would take only a couple steps, but largely because of how annoying the derivative on top would have to be with a square root, I would always just jump straight to this type of argument. Because that type of argument, you know, is only going to be a few steps. Now, the limit as x goes to negative infinity. As I described in the previous example, we could actually go through this with a similar type of reasoning to before. But dealing with the negative and the square root is a little more subtle here. And I find it more complicated than it has to be. And because of that, I like the graph transformation better. The graph transformation method I described before, I like that more because of an example like this. In the textbook, in section 4.6, I believe it is, they go through a limit to negative infinity like this with multiplication. So what I'm describing is a different method than the textbook, but I like it more. So what we'll do is turn it into a limit as x goes to positive infinity. And we will do that by replacing all x's with negative x's. Notice here, what's under the square root stays the same, because negative x squared again is x squared. But in the denominator, well, 4 stays the same if you replace all x's with negative x's. But negative 3x, if you replace that x with a negative x, you have 2 negatives, which make a positive. So to turn this into a limit to positive infinity, replace all x's with negative x's. The only real difference is in this denominator. That negative 3x became a positive 3x. And then this limit to positive infinity, you compute as before, divide everything by x. Limit as x goes to positive infinity. 2 plus 5 over x squared under a square root, all over 4 over x plus 3. And then as x goes to positive infinity, we get 2 plus 0 under a square root over 0 plus 3. So you get 2 over root 3. And notice here, these two limits are different. So, how did I phrase it here? Well, I'll say so. Y equals root 2 over 3. And y equals negative root 2 over 3 are the horizontal asymptotes for f of x. I'm not going to write for f of x. I'll just leave it. So those two are the horizontal asymptotes. So you can see in these two examples, the L1 and L2 in the definition of horizontal asymptotes, they could have been equal. They could have been different. They also could differ by more than just a negative. I mean, like take this function, just lift it up 10 units. You'll get that plus 10 and that plus 10. So they don't necessarily have to be symmetric about 0. But to find the horizontal asymptotes, you do have to consider both limits. And sometimes they will be the same. Sometimes they will be different. Now, these vertical horizontal asymptotes, these don't really belong with derivatives. But since they use L'Hopital's, or you could use L'Hopital's rule on them, they fit in the derivative section pretty nicely.